I am now recording. We're gonna be going over sorting algorithms today and basic sorting algorithms. These are things that are really important to know, but they're not very important to know exactly how they work and exactly which one you should know for competitive programming. Um, it's good to know how they work, and it's good to know when each one is used. So we have two examples here. So first, let me actually make this slightly bigger. So what we have here is merge sort and quicksort, as well as we're going to go over binary search later. So to start off, I'm going to talk about what exactly a sorting algorithm is. It's in the name. It basically puts the elements of an array or any data structure or any data structure that the algorithm is made for into a sorted order, whether that be ascending, descending, or based on something else. And there's a ton of different sorting algorithms that we don't have, and honestly, we don't have the time or effort to go over every single one. I don't even know about more than a couple. There's a few important ones. There's a few inefficient ones like bubble sort and insertion sort. And then there's a few important ones that we're going over like merge sort, quick sort. There's a bunch of others that we may be going over later like heap sort, etc. But just a reminder that these aren't the only sorting algorithms and that each sorting algorithm has its own uses and its own efficiency. So starting off, we're going over merge sort. So what merge sort is it's basically taking an input array and putting it into chunks. What that means is that each chunk is split in half. It's basically splitting each array in half. And then what you do from there, you split that array further into halves. And as you can imagine, at some point, pretty quickly for any input array, you get to a point where all the chunks are either size 1 or size 2. And to sort something that is 2 elements long, all you need, or rather 1 element long, it's already sorted. But 2 elements long, you basically check which one's greater. So for example, in this diagram, we have 38, 27. They get split up into 38 and 27. And then when you put them back together, you check which one is bigger. It's going to be 38. So you put 27, then 38. And if you're doing, instead of ascending order, descending order, you just flip that and put 38 and 27. Now, that putting it back together, that's called a merge. And that's where the name of that sorting algorithm comes from. Basically, once you have these sorted fragments of the array, you can continuously recursively merge them into bigger and bigger chunks. So as you can see, this 2 sets of 2 become 1 set of 4 that is in sorted order. And how this merge operation works is it actually goes over each element of each sub, or I guess I call them chunks. And whichever one is smaller, it checks. Right now I'm checking between 3 and 27. 3 is smaller, so I put 3 first. Then I'm checking between 43 and 27. 27 is smaller, so I put 27. Then I'm checking between 38 and 43. And since 38 is smaller, I put 38. And then last, there's only 43 left, so we put in 43. Here, since 10 is only one element here, it's basically checking 9 and 10, puts in 9, then 10 and 82. So then it puts in 10, then just 82, so it puts in 82. And then as you can see, it does the same exact thing for these bigger fragments until it has reassembled completely that input array. Now, this is completely sorted. As you can see, it seems like it's not exactly that fast. It seems like it's doing a couple of extra things when it splits it up into these chunks. But in reality, what it's actually doing is the ideal perfect sorting algorithm couldn't run in anything more than O of n, if you think about it. If you have n elements to sort, you need at least n operations just to check if they're in sorted order. So the perfect ideal algorithm, which doesn't actually exist, would run in O of n. What we have merge sort running in is O of n log n. And that we went over in our time complexities lesson. You can check that out on YouTube if you missed it. But O of n log n means that it's n times the log of n. And in this case, it's base 2, log base 2. Since we're splitting it into halves, that means that for something like this is 6, 7, this is 7 elements long. Let's just say that's basically 8. Log base 2 of 8 is 3. So 3 times 7 is around 21. So this could run in around 21 operations. That's just off the back of my head. It's probably slightly different, but it's between probably 18 and 25 operations there. 21 is the most likely one. Now, there are 2 ways to implement merge sort that are really like important, I guess you could say. Sorry, I haven't been checking the chat yet. And so the 2 ways to implement merge sort are in place and I don't know what you call it, not in place, but
that's just recursive like method.
Yeah.
Usual recursive space inefficient method.
Yeah. So in place means that basically what we have here is one array length 7 in memory. And we talked about space complexity as well. So this is 7 integers basically in memory, however big integers are, whether it be 2, 4, 8 bits in the language you're using. Let me just submit this guy. Yep. Okay. So the problem with a lot of merge sort, like basic merge sort implementations, is that they have to create a new array for the sorted array and copy elements from the original array to the sorted array. And since you have 2 different arrays in there in the program, you can think about it as double the space in memory. Now, for 7 integers, that's just 14 integers in all, sorted memory in arrays. So that's like basically nothing for computers nowadays. But if you had something more like 1 million integers or 2 million, 1 billion, whatever, you can see how just even adding times 2 would make a really, really big memory allocation, maybe that you didn't want. So in-place sorting is basically a specific implementation of merge sort, where you have the array it's going to be sorted without creating a duplicate array. Everything's going to stay in that one array. Now, the second sort we're going to go. Okay, so what we have here on the website is basic implementation of merge sort. I'm not going to go over all of it in specific detail.
Yeah, because
but honestly, if you want to go over it, yeah, it's on the website.
Just don't really worry about the code. Just worry about the idea. As long as you have the idea or the concept behind it, it's pretty easy to pretty easy to understand and how to use the function if you ever need it for competitive programming. Most people actually have templates that include like just what kind of algorithms they usually use, and this just allows them to just easily do a problem. So just don't even worry about the code. Just like focus on an idea.
I'm gonna I'll just go over just like the basics, basically explaining it as if it were pseudocode. What it's doing here is first it's checking the easiest case, where if the array is just empty or length 1, it's already sorted. So you just return it. Now, if it's not, that means that we actually have to do sorting operations on the array. And what this is doing is that it's splitting the array into halves. So it says the length of the array divided by 2. And now the double division in Python means integer division. So instead of like an odd number over 2 being something 0.5, it would just be without the 0.5. And then the second half is stored in the variable G2. And then basically it's merging G1 and G2 after you sort G1 and G2 each. So as you can see, it calls itself on G1, it calls itself on G2, and then it merges them. Now this merge operation is basically doing what I said when I was going through combining these fragments. It's pretty complicated looking, and it's kind of annoying to explain line by line, so I won't explain exactly every line. If you have a question, you can ask anytime. But it's basically, the gist of it is that it's just merging two fragments into a sorted fragment. And eventually those sorted fragments will be merged into the reassembled array. Now we have the second sort that we're going over today. This one is arguably a lot more important than merge sort, because you're most likely going to be using this a lot more than merge sort. Actually, that's a good point I should get to before I actually dive into merge sort or into quicksort, where merge sort and quicksort, I didn't get to it yet, but quicksort is in O n log n. Merge sort is also in O n log n. Most other sorting algorithms are either slower than or equal to O n log n in their time complexities, which means that most likely you're going to be using the merge sort or quicksort implementations in whenever you're using a sort. Whenever you use a sort in Python or in C++ using the built-in sorts, I think they all use some optimized variation of quicksort, which uses some optimizations to, like, some heuristic optimizations we won't go over. They're just in the implementation. And basically all you should know is that the language you're using has a sort method built in, most likely. And you should know which sort method that is, because some of them have some quirks. And some of them may be better depending on different data sets that you're sorting on. So let me go over quicksort. Quicksort is, I think, compared to merge sort, I think it's slightly more complicated to understand at first. And the implementation can be a lot more, I guess, convoluted than merge sort, in my opinion. But it's a lot more relevant than merge sort, even though they're both very relevant. I'd say quicksort is more relevant because it is slightly faster. I'll go over that in a second. How quicksort works is that it basically does the same divide and conquer approach as merge sort. So what merge sort does is it divides each array into subarrays and then conquers by basically sorting those subarrays recursively, merging them, etc. Quicksort has a similar idea where instead of dividing the array in through the middle, it takes a pivot that is determined in basic implementations.
You can just determine it anywhere.
Yeah.
Basically, you can have it set it to. But this is a factor that determines how fast your quicksort algorithm is going to be, and he's going to talk about worst case scenarios and best case.
Yeah. So basically, the pivot can be decided randomly throughout the array. So theoretically, you could have a pivot that's like at the, if we take this array, for example, this 38, 27, 43, you could have 27 as the pivot. And then you'd run quicksort on the subarray of 38 and the subarray of 43 to 10. And that pivot would be not in the middle. The middle pivot would be 3. Now, what we do with the pivot is we use quicksort to put all elements that are greater than the value at the pivot point below the pivot, or rather before the pivot, and then all elements that are greater than the pivot go to the right or after the pivot. What this means is that if we had a pivot of 27, everything in this subarray, if we had a pivot, let's say of 43, everything in this subarray is already less than 43. But in this subarray, there's a lot of things that are not all greater than 43. So 3, 9, and 10 are all greater than 43. So we want to move 3, 9, and 10 to this side. So in the end, it'll be something like 38, 27, 3, 9, 10, then 43 because we moved everything to the left of 43. And then lastly, something that's greater than 43, which is 82. And then we're done with that array. And you run, once you have that kind of sorted, in a weird way, sorted, semi-sorted rather, halfway sorted array, we run quicksort on each half of that array, each side of that array rather. Now, the way the pivot is chosen is actually really important in quicksort implementations. There's a bunch of heuristic methods, which mean heuristic as in a different way to choose the pivot that actually can significantly decrease the runtime of quicksort. Now, since it doesn't work for every single array and it doesn't work for universally for every single array in the same way, because quicksort has that element of randomness in it, we don't say that the average runtime is lower than O(n) log n, or the maximum runtime rather. Rather, we say that the lower bound of the time complexity that quicksort runs in is lower than the lower bound of the time complexity merge sort runs in. Now, that means that quicksort is, for all purposes that we're concerned with, it's pretty much just better than merge sort. Although there are lots of cases where if your data isn't just numbers and it has other properties that are already in sorted order, merge sort will preserve that sorted order. So I can go over that after the lesson is over, if you have questions about what that exactly means.
So yeah, like this is important, like the pivot, just choosing the pivot is important because even though quicksort is an algorithm n log n, at some case, if you choose like, let's say for example, you for some reason already have a sorted array and you choose to pick, you choose to run quicksort on this array. That means that if you choose to pivot as the first element, it will make it so each time you run the algorithm, the first element is going to be the minimum, and you're going to have to like compare. You're basically just comparing, and it's going to be useless. And this means, therefore, that in the worst case, quicksort can just be the same as bubble sort in terms of efficiency.
Yeah, so if you pick your pivot point really badly, it's going to run in the same runtime as bubble sort, which is, I think, an n squared, right? N squared time complexity.
Yep.
Yeah. N squared, for obvious reasons, is a lot more than n log n. It's like, for example, I think I calculated this to run in around 21 operations. N squared for 7 would be 49, and that's for a small number. That's like more than twice as much just for a list of length 7. So you'd really want to not have something that runs in n squared time for the most part. Obviously, there are exceptions, and if you know what you're doing and you know your input data, n squared might not be the worst choice. But for all intents and purposes, it pretty much is. Finally, we thought it would be pretty important to go over binary search, which is not exactly a sorting algorithm by itself, but it's something that you can make use of once you have a sorted array. So what binary search is that whenever you need to find an element in an array. So suppose I have an array that has a list of people, and each person has a name and an age. So if I want to find the person with age 20, I can either go through that entire list and find which person is of age 20 by comparing, by just checking their age every time I go over until I reach the end of the list. I must have found someone with age 20, or someone with age 20 isn't in the list. Now, binary search works by basically speeding up that search operation, but it's kind of situational in that you have to have a sorted array already. So if you have an unsorted array, it might just be faster to go through the list one by one. But if you have an array that needs to be sorted or that is already sorted anyway, then binary search is probably, it's definitely your best bet. So what binary search does is it's kind of similar in concept to merge sort because it splits it in half. It splits the array in half, checking the middle value of the array and checking the value you're looking for. So suppose I had an array of just something really simple, 1 through 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then the middle value would be 5, and I'm looking for the value 8. So 8 is greater than 5. So I split the array in half at the value 5, and then I check the elements of the subarray that is 6 through 10. Since I know 8 is greater than 5, I know that 8 must be in that subarray of 6 through 10. Now, 6 through 10 would have, okay, 8 is a bad example. Let's do 9. Same reason. Same thing will happen. It'll check 6 through 10. And then it'll run binary search on 6 through 10. So the middle of 6 through 10 is 8. Now 8 is less than the value we're looking for, which is 9, which means we have to look between 9 and 10. Now, splitting an element or an array of 2 elements long is dependent on the exact implementation, but a lot of binary search, if they have just 2 member long lists remaining, they'll just check each element individually. But suppose I split it and I got 9 as the pivot point or as the middle point of 9, 10. That means 9 is the current value and 9 is the value we're looking for, so we found it. Now, if I'm looking for 7 instead of 9, we look at 5. 5 is less than 7, so we look at the subarray that is greater than 5, so 6 through 10. Once we have 6 through 10, we go to the middle of that, 8. Now, 8 is greater than the value we're looking for, which is 7. So instead of going up in the second half of that subarray, we're going to the first half. And the first half is 6, 7. Like that array is 6 and 7. And then once we get that, it's pretty simple that we have 7 there, right there in front of us. So basically, it's a recursive array that runs in the same way that this kind of merge sort operation runs in. Now, this is actually a really, really good visualization of binary search, like this first part of merge sort, except for that, suppose we're splitting down the middle. Suppose 2 things. This is in sorted order. Just pretend these numbers are 1, 2, 3, 4, 5, 6, 7. The first problem we see is that this number right here would be the middle, but it's also being put into the first half. We want to disregard this number since we know if this number isn't equal to the number we're looking for, then we can safely ignore it and move on to either looking at the first or second half. That's the first problem. The second problem is that once we get to this stage, we need to we're basically splitting it in half. We're basically looking at it like this and this. That's not exactly how binary search works. So since binary search is pretty easy code-wise, I think it's all right. Oh, sorry, I forgot to mention, I'm not going to be going over the specific implementation of Quicksort here. It's quite similar to merge sort, but it's just using this pivot method. I don't think that anyone really would have questions on the actual implementation since the explanation is basically all the concepts. But if you want to know about the heuristic methods I mentioned for the pivot point, or you want to know about something that you didn't understand in this code segment, just ask at any time in the chat right now or anytime later, whatever you want.
And just to like prep, I think next week we're gonna do sequences and maybe trees. If so if you have any questions or just email us or just email us. I think that's the general consensus.
All right, so I saw someone just joined just now. If you missed a bunch, but I can go over it with you afterwards. Just hang in there.
Or if you don't want, you can always watch the YouTube video. This should be a quick upload. We didn't take that long. It was just basically a 15-minute class. And yeah, just any.
Yeah. Let me just go over the binary search real quick. For anyone that wants to see how this runs in real time, I could try right now just extending this to have debug statements, but let me first run through it.
Um,
Yeah, go ahead.
I think a really cool thing is if you're really interested in how, like seeing how these sorting algorithms work in real time, there's like a lot of visualization websites you can use that just really allow you grasp how fast and how like just how the algorithm works. And it's a really nice resource.
Yeah, so I'm just looking through this, or rather, I'm putting in a basic array of 1 through 12, which is in sorted order ascending. Into this binary search method we have, as always, we have the code examples on the website, and you can actually edit them and run them yourself like I'm doing right now. So if you ever want to tinker around or see how things work, you can do that yourself. But suppose we're looking through this array, which I've named x, and we're looking for the value 8. And start and end are basically the current values that were like the current subarray. So start would be 0, end would be the length of x, so that we look through the entire array of x. Now, this should work. Oh, I see. There might be.
You're not running the method.
What?
I was going to say you're not running the method. You're running a print statement with all the parameters.
Oh, yeah, you're right. Forgot to put that in. I can't seem to run it. There might be a problem loading it, and I don't particularly want to reload the page right now. I'll get to it later, but basically, I'll run through it in using the human compiler, which is me, or interpreter. And basically, what this is doing is first, it's checking if start is greater than end. In that case, that means that the subarray that you're looking for has somehow messed up in a way that means that your element isn't in the array. It's basically saying that we've looked in the entire array and your element just wasn't there. So I'm going to return -1 since index -1 means is basically an error. Now that's basically just an error check or not found check. After that is where the real array algorithm starts. First, using the same notation as before, we find the middle of the subarray that we're working on. So since the initial subarray is the entire array, 0 plus end is 0 plus the length of x, which is just length of x, divided by, or integer divided by 2, which means the middle of the entire array. It'll give you that index. That will be the middle of the current subarray. Now, it first checks if the element at the current index is equal to the value we're looking for. In that case, we found our value that we're looking for, and we can successfully return that value, or that min index. Now, the second case is that the element is less than the value at the middle of our array is less than the value that we're looking for. That means that the array, oh, sorry, my throat's getting a bit dry, but the array that we're looking for, or the value that we're looking for, would be in this subarray that is in between the start of the subarray and the middle, which means the first half. That's because the element we're looking for is less than the middle. So if we're looking for 3, 8 is the middle, suppose. I think 2, 3, 4, no, sorry, 7 would be the middle, right? 3, 6, 3. Okay, yeah, 7 is basically the middle here. There's an even number, so there's no perfect middle. Okay, since we're doing integer division, 6 would be the actual middle. So 3 is less than 6. So we look at start. So this is, 6 is the index that we're at. We already know that the index that we're at is not equal to the value we're looking for because of this check right here. So that's why we do -1, which means that we exclude 6 from the search and go here. Now, the middle of this subarray, 1, 2, 3, 4, 5, is 3. So once we get to this point, it's going to check if 3 equals the array at mid, which is also 3. So that if statement would return true, which means that it would do a return mid. So it would return the index of 3, which is 2 in this case. Now, if we were looking for 4 instead of 3, it would go to 3. It would check if this is true, this is not true. So check if this is true. 4 is not less than 3. So it'll go to finally this else statement, which is basically, this else statement can be thought of the same thing as writing this, since that's the only other possibility. But for conciseness, just that's basically best practice to have an else. It'll actually run one less if statement, I think. So now that we have that else will be true. So let me just, this will be true because 4 is greater than 3. So it'll return the binary search of mid plus 1, where mid is 3. So 4 plus 1 is 5. And then end. And end is, in this case, 5. Since end has been set to mid -1 from the previous recursion operation or recursive operation of binary search. So now that we have 4, 5 as our subarray, we use the same split method. Since the split, the integer division of 2 would be 1. Wait, yeah, it would be 1. No, the integer division of 0, 1, 2, 3, 4. So 3, this is at index 3, this is at index 4. 3 plus 4 is 7. 7 divided by 2 is 3.5, but it's integer division, so it's only 3. So 0, 1, 2, 3. That means mid would be the index of the 4. Now it checks if the element we're looking for, which is 4, is equal to the array at the mid index, which is also 4. That is true. So finally, we've got to this 4. And we return the index. Now, if we were looking for the 5, that is not true, and it basically has to run one more iteration of binary search until it finds that 5. Yeah. So that's actually it for this lesson. It was a little bit shorter than our previous lesson or 2, but I think it's just as important because these sort methods are really good. Actually, they're pretty much mandatory to know if you're pursuing anything in computer science. And they're also just generally useful for competitive programming as well.
Not entirely true, but if you definitely need to know binary search. That is the most important thing on this page.
I would suggest binary search.
Yeah,
honestly.
So if there's one thing that you need to take away from this, it'd be binary search. But hopefully you take away more than one thing. I think quicksort and merge sort are very, very important too. Yeah. If anyone has any questions, you can ask them right now. Okay. So.
No, there's no benefit because he has a return. So if it goes through that if statement, it'll just return anyways.
Yeah, so basically what's happening here is so you're basically asking what's the difference between writing this and if I put this back to else, writing this, right? So the difference here, I guess the first thing is that they're basically the same. I think that in my opinion, I kind of like this syntax slightly better, to be honest, because it shows that this only occurs if this is false. But basically, why it doesn't really matter in this case is that if this is true, this never happens since it immediately returns. if this is false, then this if statement runs anyway, no matter what. And if we have elif, if this is true, this returns anyway. This returns instantly anyway without running this check. But if it returns false anyway, it just does the check. So it's not like it's getting a defined benefit. On the other hand, if I did something like this, now here, this is technically a performance impact, because first it checks here. If this is true, it returns immediately, doesn't do any of these if statements. If this is false, it'll check here. If this is true, it returns immediately, doesn't check this if statement. If this is also false, then it also runs this if statement. However, if this is false, then we know for sure that whatever is inside this if statement is bound to be true. So basically, by the time we're running this, we're 100% certain that it's going to return true anyway. So else is not doing the check, so it's slightly more performant. Now, internally, I don't know exactly how if Python actually optimizes any parts of its programs, but internally, I don't believe so. So in Python, this might actually be, it does?
I'm pretty sure it optimizes things as you run it through the.
Yeah, I wasn't 100% sure since Python is interpreted, right? But in a compiled language like C++, something that's equivalent to this would be, even if you had an if statement like this, the compiler would internally simplify it down to just an else statement, I think. That might not be true because it might not be smart enough to do that.
Yeah, I
don't
searched
think
up
it's-
online. It appears it does. After it interprets it, it optimizes it.
Okay. So in most cases, you shouldn't worry too much about like a performance impact that you might have from this, but honestly, it's just good coding practice. And yes, it could have performance impacts later on. Yeah. If anyone else has any questions about binary search, quicksort, merge sort, or any other sort, or anything that we went over in the previous lesson, you feel free to ask. Otherwise, I'm going to stop the recording soon, and I'll go over some of the earlier stuff with the people who came late.
Link over Trump sort.
No problem. Okay. And reminder, I think that our next meeting will be next Tuesday. So look forward to that.
I mean, I heard a no problem.
What?
I heard a no problem. I asked, can we do Trump sort?
Trump sort? I don't know what that is.
Well.
Okay. So if you want the notes, quickly, I'll just paste them into chat. Otherwise, the link is on the website. It's on, you can just access it through the styccc.com. It's in the sorting overview tab. Otherwise, that's pretty much it. Thanks for attending.